Okay, so for our first example of finding the volume of a solid of revolution, we're going to look at an equation y equals the square root of x. It's going to be bounded by y equals 0, which is the x-axis, and the vertical line x equals 4. So all those things are given, and we're asked to find the volume of a solid with those boundaries when we rotate that area around the x-axis. So if you can visualize, I tried to shade in the flat area for you. And if you visualize that being rotated around, it might look like the end of maybe a ballpoint pen or the shape of a bullet, something like that. So what we will do, if you've looked at any of the material that I've given you, we're looking at finding basically the area of a circle and then multiplying that by an infinitely small height, and that shape that's being formed, if you would just use this line that I've drawn right here as the beginning of it, this would be the radius of a circle that would be formed if you flipped that flat shape around and around and around. And so that radius, that line that I just drew in, needs to be defined for this problem. And so for this problem, that radius is going to equal the function that we've been given. So in this case, that's a measurement from the x-axis up into the function, which is the square root of x. So to find our volume, we will do pi times the integral. Now we're going to integrate along the x-axis from 0, which is our first boundary, to 4, our second boundary. And then our radius, which is the square root of x. And remember, on a circle, it's pi r squared. And then since we're actually doing a cylinder, then we'll take it times the height, but that height is infinitely small. And that's where we get dx. And so we'll do the actual work now. Simplifying, the square root of x squared would just be x. So we're actually just integrating the x. And now we'll do the actual integration using your power rule. So the volume will equal pi times, and then the antiderivative of x would be x to the second over 2. That's evaluated from 0 to 4. Then we'll make our substitutions and have 4 squared over 2 minus 0 squared over 2. And that's going to give us 16 over 2, which is 8. So 8 pi. And again, that's the volume of the shape that would be found if you rotated that flat surface around the x-axis. Okay, so we're going to take our second example here and look at what happens if instead of rotating around the x-axis, we rotate around the y-axis. So I've given you as boundaries a line, y equals 6 minus 3x, and then the x and y axis, so y equals 0 and x equals 0. So if you think about flipping this flat area around the y-axis, I think hopefully you can visualize that you would get a cone shape. And so we're going to find the volume of that cone that is formed. Now, when you rotate around the y-axis, then the discs that are formed are going to be measured from the y-axis over, which means that instead of having functions in terms of y equals, you're going to have to solve them for x. So we're going to, first of all, have to take y equals 6 minus 3x and solve it for x. So you could minus 6 and then divide by negative 3, and that's going to give you negative 1/3 y plus 2 equal to x. And that is going to be the measurement of this radius that I've drawn in for us. So in this problem, our radius, because we're rotating it around the y-axis, will be negative 1/3 y plus 2. So we're still working on a disk, which is essentially a very flat cylinder. So our volume is going to be found by doing basically the volume of a cylinder. So pi. Now we're going to integrate, and this time we're integrating with respect to the y-axis. So we want to be sure that we use our y endpoints. So from 0 to 6, and then the radius squared, so negative 1/3 y plus 2 squared, and then to get our height, dy. And so we'll have to do a little work on this one. We'll have to square out the negative 1/3 y plus 2. And so if you do that, I'm going to go ahead and do that for us. That's going to give us 1/9 y squared minus, and then our middle term is going to be 4/3 y, and then the last term is 4 dy. And then after that, we can do the power rule. So the power rule for us would be volume equals pi times, and so 1/9 y squared. That's going to end up being y to the 3rd over 3, and then you'll multiply that by 1/9. So we'll get y to the 3rd over 27, and then minus, now your 4/3 y, your y would be squared and then over 2. So you'd be able to reduce and get 2/3 y squared, and then your 4, which would be plus 4y, evaluated from 0 to 6. All right, so that volume is going to be pi times, we're going to substitute in 6, so 6 to the 3rd over 27 minus 2/3 times 6 squared, and then plus 4 times 6, and then the 0 plugged into everything will just be 0. And simplifying all of that, you will end up getting pi times 8 minus 24 plus 24, and you end up getting 8 pi for your volume, which is just a coincidence. It's what. Okay, for our third example, we're going to look at the same setup actually as example number 1, but this time we're going to rotate around the line x equals 4. So if you think about that, if we're rotating around that line, you'll get a completely different shape than what we had previously. So we're rotating it around this vertical line, x equals 4. And so that presents the problem of identifying how long this line is. And that line is the radius of the circles that would be formed on top of the discs. So we can't just use the function this time because the function is actually a measurement from the y-axis over. So we're going to have to do a couple of things. First of all, we should take care of the fact that we need to solve for x. Since we're going around a vertical line, we need to get it in terms of x. So we can square both sides. Y squared would equal x. So x equals y squared. And that description, x equals y squared, is actually a description from the y-axis to the function. So if I wanted to know the length of that blue line segment, that would be y squared. And likewise, if I wanted to describe from the x-axis, or excuse me, the y-axis all the way over to the vertical line, that would be 4, because our vertical line is at x equals 4. So hopefully you can see that the black line segment that I've drawn, the radius that we want, is actually taking the 4 and subtracting away the y squared measurement. So the radius that we're going to use in this problem is 4 minus y squared. And really, that's probably the most difficult part of the problem. So now you're going to do the volume, which is pi times the integral. Now, again, you're doing the y values, and those must have gone away as I started writing. But we have 0, 0 here, and then this point is the point 4, 2, and that's the highest y value that we get. So we'll be integrating from 0 to 2, since we're doing a vertical rotation this time. And then the radius, 4 minus y squared, we'll square that, and then dy, getting the infinitely small volume of our disk. So that would be v for volume equals pi times the integral from 0 to 2. We'll have to multiply out. So that would be 16 minus 8y squared plus y to the 4th dy. And next we'll do the power rule. And so we get pi times, and that would be 16y minus 8y to the 3rd over 3, and then plus y to the 5th over 5. We're going to evaluate that from 0 to 2. So substituting in, we get volume equals pi times, we'll have 16 times 2 minus 8 times 2 to the 3rd over 3 plus 2 to the 5th over 5, and then plugging in 0 would just be 0, and your volume ends up being, after you simplify, 256 pi over 15. Again, that is rotating it. All right, for our last example, we are going to be rotating a shape that is bounded by y equals x squared plus 1 and y equals 2. We're going to be rotating that around the horizontal line y equals 2. So because it's a horizontal rotation, we can leave everything in terms of y equals. And I've drawn the radius line that we're going to need to define in blue. So we're going to look, first of all, at going from the x-axis up to our line, the horizontal boundary, and that would have a distance of 2. And then looking at going from the x-axis up to the function, and that's going to have a value of whatever the function is, so x squared plus 1. So if we're going to define the length of the blue segment, that would be the total distance of 2, and subtract from that the function distance, x squared plus 1. And so our radius is going to be negative x squared plus 1. And so we'll do the volume, doing pi times the integral. Now we're going with our x's, so from -1 to +1, and our radius, negative x squared plus 1, that is squared. And then, of course, the height of the disk, infinitely small, dx. So our volume would be, now, I'm going to notice that this is symmetrical. So rather than going from -1 to 1, I'm going to integrate from 0 to 1 and just double my area. And I'm going to go ahead and square out the negative x squared plus 1. So that will give me x to the 4th minus 2x squared and then plus 1 dx. From here, I'll do my integration. So the volume would equal 2 pi. Again, that's doubling using symmetry. I'll have x to the 5th over 5 minus 2x to the 3rd over 3 plus 1x, evaluated from 0 to 1. And plugging in our values, we'll have 2 pi. We'll be plugging in 1. So 1 to the 5th over 5 minus 2 times 1 to the 3rd over 3 plus 1 times 1 minus 0. Plugging in the 0 gives us 0 everywhere. And simplifying this and getting common denominators, you would end up getting a volume of 16 pi over 15. And again, that's the volume of taking that shape and flipping it around the y equals 2 horizontal line. So the shape you might get there, maybe something like a blimp, if you could visualize that. So 16 pi over 15.